Hey there, everybody. I have a quick example here, similar to a lot of textbook problems. Approximation techniques for integration. There are times when it is just outright impossible to integrate certain functions. So we can approximate them pretty accurately by either the trapezoid rule or the midpoint rule. In college, you might learn Simpson's rule, which is totally awesome. It's using sections of parabolas to approximate more accurately. It's actually quite a bit more accurate with fewer subsections, but we're sort of stuck with trapezoid rule and midpoint rule. You use this little t with a subscript to say how many slices, how many intervals you're using to approximate. So this t sub 4, you'll see in our textbook, I think you have one that's t sub 8, so you're going to use 8 subintervals. We're just going to go from 0 to 1 because this thing gets so darn big, it gets really unwieldy, very, very large numbers when you're even squaring 2 and then raising e to that exponent. But we'll keep it simple here. So I've made a little table and filled in our trapezoid rule points where we're going to have a first point and then a quarter point, a half point, a three-quarter point, and a full point. And then the way we do it is the first point is only counted once, and then of course we're counting the second point twice because it's both the upper base of the first trapezoid and then the lower base of the second trapezoid, and so on. So this is a simple pattern where you find each of those values. You're going to multiply each by 1, then 2, 2, 2, and the last one by 1. I take these numbers, I add them all up, and I multiply by the width of the interval, delta x, which in this case is 1/4, and then we divide it by 2. That's really the averaging of the bases for any trapezoidal area. So just remember it's delta x over 2, and in this case that's 1/8. So I add these all up, I divide by 8, and I get 1.4675. You can check all that. I'm just doing it longhand, so I think it's pretty good, but you can check it. Then this is, of course, just the way we would write that integral. Here is the midpoint rule for this same function. Now, the midpoint are those halfway between each quarter. So that's 1/8 and 3/8, and then 5/8 and 7/8. There are the decimal equivalents of those midpoints. And here's the function value of those midpoints. Now these we just add up because that's the height of each approximation. Each rectangle will be, that height, and there's the height going through that midpoint like that. And then the width is just our 1/4. So I add those all up, divide by 4, and this is what I get as the approximation here. Okay, so now those are just approximations. We can actually graph it on the calculator and see what it looks like. Here is the graph. There is the integral. I can do it again just to verify. If I go to second trace, as you know, 7, the lower limit is 0, the upper limit is 1, and will it refill that in? Oh, it doesn't even refill it in, but it shades across there, of course. Whoops, and there it is, 1.4626. 517 for a few more decimal places of accuracy. And you can see we're really pretty close. How close are we? I think that we're within about 0.003 here, and 0.4. We're a little less accurate there, but also pretty close. We can get a sense as to what we are guaranteed for accuracy by looking at the error bound, and that's what this step process is right here. I know that my error is going to be bounded by these two formulas. This is for trapezoid, this is for midpoint. Guess what? The larger number in the denominator for the same exact formula means that this is going to be more accurate, twice as accurate as the trapezoid rule. Because the midpoint, you get that above and below, and they kind of cancel each other out more. For our recent example, that's concave up. So we're going to be getting underestimates with the trapezoid rule, whereas the midpoint rule, like I said, a little bit more cancellation, we're likely to be more accurate. So the formula goes like this. We need to find this k value, and this is the most difficult thing. And it has to do with the shape of the curve. You're going to be less accurate the more kinks the curve has in it, and the broader the width that you are, the interval that you're finding the area over. This k is simply defined as being the largest value that the second derivative of the function can take on over that interval. So here's my function, e to the x squared. My first derivative, good old chain rule, you bring out the derivative of the inside, it's 2x. My second derivative, I have to go to a product rule and a chain rule. So here's my ABBA product rule. First times the derivative of the second is just 2, plus the second times the derivative of the first. We've already got that. So it's 2x times that bit with the 2x. So I wind up with this as my second derivative. Now, if I plug in my two endpoints, it's very, very likely that my endpoints, you could certainly graph this on a calculator, look at the pretty picture, you'll see that it's increasing as x increases. So my 0 starts off at 2, and my 1 value gives me 6 times e. So something around 16-ish, 15, 16. E is slightly less than 3. So I know that my k value is going to be 6e at the very greatest. So that's what goes in right here. So my formula then becomes 6e for k. The width of my interval is just 1, cubed is just 1. Then 12, and then that's my number of partitions, my number of rectangles in my approximation. So as that gets larger, my error goes way down. So here is me just doing the math, and I wind up with an error bound of 0.08. So you can see 0.08 is much more accurate than 0.003, but this is mathematically what we're guaranteed to be within this level of accuracy. Here's the next one for the midpoint. Again, it's more accurate. I go from 0.08 to 0.04, twice as accurate, half the error. And again, that's borne out by the actual approximations I found earlier, okay? Many times we have a certain tolerance that we want to have a physics experiment stay within a certain level of accuracy. How much data do we need? How frequently do we need to sample our experiment and take a reading of a temperature or something like that to get an accurate look at what's going on? So this is a typical kind of a question. How large do we have to make n so that each approximation is accurate to a 10,000th, all right? 3 zeros and a 1. What we do is we just go back to our equation, we set it up, and then we set it equal to that amount. Now, absolute value on either end will do the trick. In this case, when you get an answer and it's negative, you realize that we're just talking about it being like an overestimate or an underestimate. So here it is, 0.0001 equals 6e over n squared. I can just multiply both sides by n squared and divide both sides by the decimal, and I'm going to get it like this. I just crunch some numbers. I get 13,591, but that's n squared, so I square rooterize it, and I get 116. So my n has to be larger than that value. So there's the next value above 116.58. So I need quite a few slices to mathematically guarantee that I'm going to be at that level of accuracy. If I do the same thing for the midpoint rule, you'll see that my number of slices goes down, but it's going down really by the square root, so it's not going to be like quite cut in half. But there we go, same sort of math solving, and I get my n there of 83. Okay, so this is a typical problem right here, number 17. Find the approximations for trapezoid rule with 8 subdivisions, midpoint rule with 8 subdivisions for this integral. Here we've got cosine x squared dx. Estimate the errors in part A after you've made those approximations, just like I did, and then how large we have to choose n. So very, very similar to the example I just did. Good luck, everybody.